Good afternoon. Before we start the lecture today, I'd like to inform you that next Monday we will have a written quiz. So there's no lecture, but we will have a written quiz, maybe 1 hour or something like that. So because it will be based on calculations, so I like to see your calculations. So this will be so next Monday there is no lecture, but there will be just a written quiz. Okay. Today we start a new part of this machine learning course, and is related to non-parametric methods in machine learning. Non-parametric methods or semi-parametric methods in machine learning. We have already discussed machine learning algorithms that based on some pre-assumptions, like we assume that the data has certain structure. And when we assume that it has certain structure, for example, multivariate Gaussian or multivariate normal distribution, if the data originally was not based on multivariate normal, then this will be like source of biasing. So the pre-assumptions usually it can be good if they fit with the original data, or it can also source of biasing. Also in other applications that when we don't have labeling of the data, or we don't have also any pre-knowledge about the source of the data or behavior of the source of the data, then we need also to think about different methods, non-parametric methods, in order to find or to learn the data or to get knowledge from data. So this will be the topic of today's lecture, and we will see here that we will have different kind of challenges in the learning process when we don't have some like labeling, or we don't have some outcomes for training. So how could we structure the data, or how can we build some sound and useful models based on data that they don't have labels, or also how can we build some useful models without pre-assumptions about the parameters of the data? Okay, we will start with the semi-parametric, not fully like non-parametric algorithms, but we will start with the semi-parametric algorithms. Now once we have data, like for example, assume that we have some labels, some data like this. So we have some input attributes, and then we have some output. So we have attributes here like x1, x2, till xd with d dimensions, and then we might have also some classes here. That this data, for example, belongs to class 1, class 2, class 1, class 3, class 5, and so on. Okay? Now we assume that we have labels. And also we have data as it is given. Okay? This data usually is the behavior or the structure of data. We can assume that it is based on some multivariate distribution. It can be any distribution. It can be multivariate normal or whatever. Although that normal distribution is the one that we usually use. Okay, so the distribution here of this data is or could be constructed based on the groups or the classes here for each class. So here it will be the summation of the distribution of the data belongs to certain group ji multiplied by the probability of being in that group. So this is the construction of this structure of the available data. We have seen in parametric machine learning that it is relatively easy to find this, because if we started with some assumption that the classes or the distribution is multivariate normal, and then we start with each class, and for example in class 1, C1, and we collect the data in each class, and from this data we compute the maximum likelihood estimation of the mean and also the covariance, and then things becomes easy, and then we build our distribution for each class, and then we can use this as a discriminant function, and we described these things in details before. However, that it is given in this way. So this is the probability of each class, and the mean, the maximum likelihood estimation of the mean in each class, and the covariance estimation in each class. It is easy to compute, to be computed, as we have seen in parametric estimation in part 4. Now the story is different. Now we don't have those labels. Okay, so we don't have labels here. All what we have is data. Okay, and what behind this data, as you can see from this one. So this data that we have, they are generated from different groups. Group 1, Group 2, Group 3, and Group 4, and whatever number of groups. But we have unlabeled data, and what we have, we observe only the result. So we have only the data, but we have no idea how many groups behind this data, okay, or how many classes. But hey, remember, when we have unsupervised learning, usually we don't name them classes. We name them like groups or clusters. So here we have like certain n or k groups behind this data or clusters, but we don't know them. So we have no idea about each input belongs to which group or to which cluster. This is the first thing. And also, we have no idea about the distribution which formulate the data, and the distribution formulate each group, because there might be, the groups might have different distributions as well. So the problem is really challenging in how to build or how to extract information if we don't have like teacher data, or we don't have labeling of this data. Okay, so this is the topic actually. Today we like to build this function based on only the data that we have. We have, as I said, we have hidden information. The number of clusters is a hidden information. The distribution of each cluster is hidden. We don't know. The parameters of each distribution is also hidden. So usually we try to, of course, we will see that we need to put some assumptions in start to start the calculations. Okay. The first one, which might be the simplest one to start with, is named as k-means clustering. K-means clustering. How it works? We will start with the simple example given in the textbook about, they assume that they have a picture, and this picture is represented by every pixel, represented by or every dot actually represented by 3 pixels for example, red, green, and blue colors. So they can generate up to 16 million colors. It is like most of our mobile phones today, they can support 16 million colors. And they want to present this picture into another panel or display panel that it can show only 256 colors. It has also 3 pixels for each color, but it can show only 256 colors. And now we like to represent this picture into that panel with minimum loss of information. Okay, so the idea here, how to find the optimum, because here we have from M1 up to M256. This is all what we have, the colors that we can represent here. However, here we have xt, t of course from 1 up to n, because we have n pixels in the picture. But here, xt can be one of up to 16 million colors. So, and now we are looking for the best data, because we want to, when we project this original figure to this lower color maps panel, then we like to preserve the same or as close as possible to the original picture. Okay, and the first thing that we need here, they assumed in the example that they need to design from M1 up to M256 first, those vectors, and then we like to see each xi here, each pixel belongs to which one of those. So this is the example, and we try to explain the k-means clustering based on this simple example. Okay. The idea here is based on this algorithm that you should select mi which minimize the error. So we like here, this is the xt, for example, minus mi. So if we said that we should select the vector mi which minimize xt minus mj for all j from 1 to 256. So we should select the ith one which minimize the total error, which minimize the error. So this is the meaning here. So we should find the jth one which will minimize the error between the original pixel in the original picture minus the mj. Okay. The problem here in this equation that we don't have mi and mj. We don't have them. So we like to design also the mi. Mi is not exist. If mi exists, if we know like m1 to m256, it would be easy to find, because just with fast searching we can find the minimum, but we don't have those m's. What to do? Okay, before we see what to do, here we compute the total error in the picture. The total error in the picture is given in this equation. So it is double summation over all pixels in the figure, in the original picture, and here summation over all possible, in this example is 256. So it will be xt minus m1 minus m2 minus m3 until 256. What is bit? Bit is the selection parameter. So if I achieves the minimum distance, then bit equal to 1. Otherwise, bit equal to 0. So bit is the selection parameter where it selects the optimum m. Otherwise, it is always 0, 0, 0, 0 until we reach to the one which minimizes the distance. Then this is the total constructed error over the whole picture. What we need to do with this one, this should be minimized. This should be minimized. Okay, how to minimize this? Okay, this could be minimized by differentiating this with respect to mi and this equal to 0 as we know. However, and this is the tricky part, that the selection of bi depends on the selection of mi. And we don't have both. We don't have bi and we don't have also mi. We don't have this value, this vector, nor this parameter. Okay? So this is the tricky part. We need to solve this equation to minimize this equation in order to find the optimum representation of the original picture. If you differentiate this equation and make it equal to 0 to find the minimum, then you will get this result. So mi should be the summation of bi of t xt divided by summation of bi t. Again, we don't have bi in advance, and also we don't have mi. Then the k-means clustering suggested this simple procedure to solve this problem. They say simply start with any mean. For example, mi, let's say mi0. We start with a vector mi0. Anything you can start in the beginning. Of course, there are some way how to select the initial, but let us start with some random number. We start with some random number. Okay. Then we have the original picture, xt minus m. Of course, here we selected this as a random, so it means that for all I, let us say j, so we select this as a random. We have 256 ones as a random, so it is vector of random initial means. And then we find what is mi, which achieve the minimum over all j of this initial m. Okay, then we know mi. Once we know mi, then this bi t is equal to 1, and the others, of course, equal to 0. Okay, once we found all bi based on this initial guessing, then we calculate mi. We calculate mi based on the bi's that we based on bi, which is calculated based on our first guessing. Okay, now we calculate bi, then this can be repeated, because when we calculate bi, then we can repeat and find what is bi based on the mi that it has been calculated. And we can repeat. Of course, I will give a numerical example in order to explain this in details. So this is the pseudocode. The pseudocode to calculate it. So we start with initial mi, and then we select bi, which minimize the errors, and then we compute mi, and then we repeat, calculate bi, and compute mi until mi converges. So this is called k-means clustering. It is one of the simple but yet very important clustering methods that it is basis also to other clustering like expectation maximization method, as we will see later. Okay, now if you start with certain data like this, so you can see that here we have two-dimensional data, but it is not labeled, so it is all have the same color, as you can see. So we start with any initial guess of mi. So we started, for example, with the 3 m's, and after calculations, then we end up with the 3 clusters in this way. However, if you start with different location of the means, then you can also receive, or you can get different kind of clustering. So the clustering depends on 2 things. First, K is the number of clusters. Sometimes it is given, like in the example of the picture now, because it was 256, it was given. But otherwise, if it is just data, then it is based, or it can be based on guessing as well. So you need to give this the number of clusters. And second, depends also on the initial condition of the clusters means. So how to start. So it is local method, which the result depends on the initial condition or the initial clustering means that you start with. Okay, to explain this method, I gave this numerical example in order to understand how it works. Assume we have the following unlabeled data. Find by hand one proper clustering. Assume that there are two different clusters. So now we assume the number of clusters as 2. And start with M1, 1, 1, and M2 like -1 and -1. So here also I gave the initial how to start. And in this data we have x1 and x2, so we have two attributes, and this is the data given. And let us start. Okay, in the beginning I will start by computing the distance between the first entry with the first mean. So the distance here is 2.4 minus 1 plus 1.1 minus 1, and the result is 1.5. You can, of course, use also square if you like, but here I just gave the absolute value. And the distance between the first entry and the second class, or the second guess of the mean, is given by D12. D12 is the distance from first data to the second cluster mean. So this will be 2.4 minus -1, it will be +1, plus 1.1 minus -1 is also plus, and the result is 4.5. Which one is closer to the first data? Is it the first mean or the second mean? It is clear it is the first. So the first mean is only 1.5, the distance with the first, of course, here the mean is the first guess, I mean. So it is only 1.5, and the second one is 4.5. So what means? It means that we should select the first guess as the class of the first data. For the first data. And what this means that B11 means that the data for the first entry to the first class is equal to 1, or the first cluster actually. It is better to say cluster because class is for parametric classification. And B21, the B of the first data to the second class of the second cluster is equal to 0. Okay, now I compute the distance between the second data entry to both guessing M1 and M2. With the first guessing, the distance will be -6.2 minus 1 and plus 3.1 minus 1. The distance is 8.3, and the distance with the second guess is 9.3. Again, it is clear that the second data entry is closer to the first cluster than the second cluster. Then I would select that B12 equal to 1 and B22 equal to 0. Okay, the distance of the third entry. For the third entry, it is 2.1 minus 1 plus -2 minus 1. The distance is 4.1, and the distance to the second guess is 2.1 plus minus 1 becomes plus, and then -2 minus -1 becomes a plus also, and the distance is 4.1. So here is 4.1, the same distance. Then it is up to you to select any one of those you can decide. Here I decided to belongs to second cluster, the second cluster. And finally, the fourth data, again, repeated, and we find the distance is shorter with the second cluster. It is only 7. Then it becomes B24. 4 here means the data entry is 4. To the second cluster is 1 and is equal to 0. Okay? After this step, we forget everything related to our guessing, because now we can compute the means. So the mean, because we know that the data belongs to the first cluster, is the first and the second. Then I take the first data plus the second data divided by 2. This gives us the new mean value. This is like update for the new. We start with a guess, but now we have some computed mean. And also we do the same for M2. M2 also the mean of the second cluster that we can calculate it in this way. So we take the data belongs to the second cluster. In this example is the third and the fourth, and then we add them divided by 2. Then we got the mean of the second cluster. We should stop? No. Now we have M1 and M2. Then we again repeat the same process. How to repeat it? Again, we measure the distance between M1 to the first data, with the second data, with the third data, with the fourth data, and the same for M2. And in each time we select the shorter distance, and we so that maybe in the second round you will find that maybe the first data will jump to be in the second cluster, and the second data maybe will be in the same first cluster. The third data maybe it will go to the first cluster, and so on. And then we got update for the cluster means. And we don't stop, of course. We continue to calculate it again. So it becomes like iterative method until these two, M1 and M2, converges to some fixed numbers or fixed vector. Once it converges to some fixed vector, then we stop and we say that the data now has been clustered. The data has been clustered. So this is called k-means clustering. And here I wrote a code in Octave that it makes this process like automatically. However, there is also another function in Octave under statistics package is called k-means. So you can use that one, but even we wrote here some simple code in order for those who want to learn also Octave. So here you just give the input data as matrix A with dimension n by d. So you have n is the data samples is n samples, and d is the dimension, data dimension. And also you decide how many like cluster that you want. Then this code will return to you the clusters, the means of the clusters, and also the covariance of in each cluster. And as an application, I put in this code two-dimensional data, like 500 input data, not labeled like in this way. And I tried to make the clustering based on the k-means with the Octave code, and then give them in this way. And what we have here in the circle is the mean of each cluster. But when I repeat the same, but with different initial condition, it gives another kind of clusters. So the clusters might change with the initial condition or the initial cluster means that you start with. Of course, in each one, they might have different interpretation. So after making the clustering, usually experts can look to the data and they try to extract information or knowledge based on the clustering result. Okay. There's some exercise also in the model, so you can download the data here and try to also make the clustering based on the code. Okay. Yeah. One problem with the k-means clustering that first it depends on the initial conditions, as we said, and the second the patterns that it is able to cluster the data is quite simple. Usually it can cluster the data like in circles, as we have seen. So if we look to how it clusters the data, usually it can cluster the data in this way. Some data, they have some more complicated patterns. Like, for example, if we have some data in 2 dimensions, that the clusters can be like this way. For example, this is one cluster here, and we have other cluster here, for example, maybe a third cluster here. So when we have like some kind of different kinds of ellipses, okay, of the clustering. Actually, k-means many times fail to find the optimum clustering in this case. So how to generalize the k-means clustering and to have more effective and more efficient clustering method. One very well-known technique is called expectation maximization algorithm, EM algorithm. Although the general derivation of this algorithm can be a little bit like boring, but however, the concept is very simple. The concept, how it works, is very simple. In order to explain how it works, I will start with simply like one-dimensional data. Okay, so now we have like one-dimensional data in this way, and we start with the data that labeled data. So we have labeled data like red and yellow data. Okay, so of course in general that we have unlabeled data. In general that we are looking for clustering, that we are working for unlabeled data, unsupervised learning. But just to let us start with this labeled data, that we have red and yellow data, okay? And based on this data that you have, you want to learn the situation in order that when you have new data, you decide it belongs to which class. Here we have two classes, red class and yellow class. Okay, so in this case, as we know before, it is very easy to calculate or to compute. Simply that you compute the mean of the yellow class and the mean of the red class, and maybe the variance of the yellow class and the variance of the red class. Okay, like MR, M yellow, and SR square and S yellow square. And assuming that every class it came from normal distribution, of course it is not necessary. It can be any distribution, but for simplicity that let's say it is from normal distribution, that it was also given in this case. So once you have all this information, you have done. So you have already learned the situation, and once you have new data, if you have new data, you don't know is it yellow or red. Simply, I will calculate the probability that this data belongs to what is the probability that it is, if we call this data, for example, X, okay? So what is the probability that you are in red, given the data X, and the probability that you be in yellow, given data X, and then you just select the higher probability, then you assign this circle to which one. So it is simple like that. Because we have already calculated the parameters here. Based on this, we have already calculated the distribution of being red and also the distribution of being yellow, based on the data that you have. Once we compute the parameters, everything becomes easy to calculate. The challenge here, if you have these circles, no labels, no red, no yellow, how can you build some useful training or learning process based on this and such kind of data? One method is k-means. In the k-means, again, if we know that there are two classes, then we start with initial means, okay, M1 and M2, and then we start to calculate the distance for each point to that mean, and then we, after certain iterations, we will converge, and then we will have red and yellow based on that k-means clustering. However, now we are looking for more like sophisticated method. We are looking, for example, what if we know the data? In k-means, we don't need to know the distribution of the data. We start just with assuming or with the guessing of the mean, and then and this mean will be the center of the cluster, and then we classify or clustering the data. But here we like to generalize it, that in order, if we put some assumption about the distribution of the data, how this could, how like better clustering could be obtained. Okay. Um, Now, if we assume that the data is, assume that we have two clusters, so for this data that k equal to 2, and let us start, or let us assume that we know also the distribution is normal distribution of the data. Okay, so we know that this data is, of course, they are not labeled. Again, they are not labeled, but we know that they are normal distribution, and we have two classes or two clusters. Okay, so the first cluster, it has mean mu1 and sigma and variance sigma 1 square, and the second cluster, it has a mean mu2 and sigma 2 square. Okay, so now with this information that you have, so you know already the distribution of 1 and the distribution of 2, and assume that you know also, it's just assumption, you know also the parameters mu1 sigma 1 square and mu2 sigma 2 square. How can we classify the data or cluster the data in this case? It would be quite simple. What I will do, I will start with the first point. I compute again what is the probability to be with this distribution, what is the probability to be with this distribution, and then we select the higher probability, and then I start with the second one. What is the probability of B with this distribution? It is I am looking to the maximum likelihood probability in this case until I cluster all the points, and in this case I will get this result. This is the expectation maximization. So I will have that this should be belongs to class 1, and this should be belongs to to cluster 2. However, this could be the reality, of course. The reality, it might be something different, but at least this is what I can obtain from this result. But again, usually we don't have those parameters. Usually we don't have those, but we don't have the mean and the variance. Okay, we might assume that or give some assumption about the distribution, but who can give just general assumption about the mean and variance? Of course, this is not the way how to calculate it. How to do it? We can also build similar algorithm, somehow similar to that k-means iterative method. What to do here? And this is the explanation of the EM method. Expectation maximization algorithm. It is based on that. First, as I said, it is given the k, the number of clusters is 2, for example. It is assumed. The data analytics or the when the person who make that data analysis, they can start with k equal to 2, k equal to 3, k equal to 4, and then they can analyze all the results in order to find the optimum k. And also let us start that we know the distribution, though. So both of them, they are normal distribution with mu1 and sigma 1 square, and normal distribution with mu2 and sigma 2 square. However, we don't know those parameters, and we like to find the parameters that fitting this data. The idea is there. It is very similar to the k-means in this regard. So we start with some guessing of the mean. So we start with guessing of the mean, and also we guess the sigma 1 square, and we say, for example, 0, and also the second mean and the sigma 2 square 0. So we start with guessing also. Once you start with the guessing of the mean and the variance, then you start to assign each point to which distribution based on the probability. Based on the probability. So now we calculate the probability of being within the first distribution and the probability of being with the second distribution, and then you select the maximum probability and the second one as the second data, the third data, and so on. Once you classify all your data, assume that you have this point belongs to distribution 1, distribution 1, distribution 2, distribution 1, distribution 2, and distribution 1. Okay? Now we have this data belongs to distribution 1. I update the mean, so mu11 equal to what? The data x1 this one, plus x2, this one, plus x4, plus x6 divided by 1, 2, 3, 4, divided by 4. Now I have updated the mean. And then also I update the mean mu2 in the same way. So I calculated the data which belongs to the second distribution, and I updated this mean so that in order to find the better guess for the mean of the second distribution, and also we can compute the variance of each distribution. And we repeat the process again. So the first is estimation. We estimate the mean and variance, and then we maximize. How to maximize? This is the name, expectation maximization. Maximization, I assign each point again to the maximum probability, and this is the maximization step. Once we find the assignment of each point to which distribution, I repeat the process and we estimate the mean using maximum likelihood estimation, MLE. We estimate the mean again and the variance again, and repeat the process and repeat the. We continue in this way until we converge to the final convergence, where the mean, for example, the mean of I at step, let's say at step L, is becomes like minus mean I at step L minus 1. The error becomes less than or equal to some delta function that we start the design process. So when the mean increment becomes very, very small, then we can stop for the mean, of course, and the variance. So this is the process. The process is, it looks a little bit like long, but it is very effective, and it is not difficult. However, of course, if we generalize this to multidimensional data, the analysis can be a little bit more larger, as we will see in the next slides. However, I may skip the details and mathematical derivations, but what I want from you to understand the basic concept, not to go through the mathematical details, how to derive it, because they are already in packages. This EM clustering, they are already in computer packages, but it is important to understand how it works. So it works in this way. So I will repeat it like roughly. So we start with we have data. We start with initial mean. Of course, we can start the mean by using k-means clustering. So k-means clustering, when it converges, it can give us very good starting point of the means. But we start with some mean guessing. We start with some variance guessing. And we start also with some guessing of the cluster numbers. We start also with the distributions that we like to consider, and then we come to now we come to the portion of the data. We start one by one, each data element. We try to assign it to which probability distribution, to the one which has maximum distribution, based on the initial condition that we start. Okay, so now we maximize, looking for the maximum distribution for each point. Done. After that, we know that each point belongs to certain cluster. Each cluster represented by certain distribution. In this simple example, we assume that both of them, they are normal distribution, but with different mean and variance. Okay? And now each data, or we know that data belongs to cluster 1 and the data belongs to cluster 2, based on the guessing of the mean and variance of each distribution. Second step, we improve those by calculating the mean and variance. Now we don't guess anymore. The guessing is only in the first step. Now we compute the mean at iteration 1 by adding all elements belongs to cluster 1, okay, all elements belongs to cluster 1, and divided by their numbers in cluster 1. For example, we have all elements xi from I equal to 1 to n multiplied by ri. Ri is equal to 1 if the data belongs to cluster 1 and equal to 0 if the data belongs to cluster 2. Okay, and then this will improve or will be the first iteration of the mean. And also, once we calculate this one, we can compute also sigma 1 square of iteration 1, which is based on the maximum likelihood, which means that it is summation of xi, okay, minus the mean mu11 square, okay, multiplied by Ri. Ri, as I said, it is 1 if the data belongs to cluster 1, divided by N1, the number of data in cluster 1, minus 1. This is the maximum likelihood estimation. It's the unbiased version of the sigma 1 square. Okay? And the same done for mu2 and sigma 2 square. Once done, repeat the process again and assign each data to the new, because now it is updated. The distributions have been updated. Then we found, or we try to find the new assignment of each data point to which distribution by calculating the probability, and then we select the maximum probability each time. So it is simply like that. It is simply like that. And this is the way to calculate the probability. So what is the probability that belongs to R or Y? For the new data, is it in either red or yellow for this example? Based on the observation xj is given by f of the distribution of the fxj given yi, probability of yi divided by the distribution. So it is based on the Bayesian function. And in this example, assume you have the following random data. It is one-dimensional data. So you have 14 minus 1, 0, 13, 2, 18, 3, minus 4, 1, 5. Assume two clusters with normal distributions. Assume the initial mean is 0 and 5, and initial variance is 1 and 2. Then calculate EM algorithm based on 2 iterations only by hand. So if you calculate this, you will understand very well what I am doing here. It will be very clear for you what I am doing here. This is a flowchart about this the EM. So we start with some assumptions like number of clusters, initial means, data distributions, and then we assign inputs to clusters with maximum conditional probability. Then we estimate the parameters of each cluster based on the assigned data. Then we compute the increment in the parameter. Here, in this case, mean and variance. And we check, is it converged? If yes, we stop. If no, then we assign again. So this is the maximization step, estimation step, maximization step, estimation step. All the time, this is the name it comes that like expectation and maximization method. It comes from this process, this like iterative process, until we converge to the solution. As I said, the same method, when we like to generalize it, not only to one dimension, so to n-dimensional, and also not only for the normal distribution, it can be for any distribution. So the mathematical derivation is slightly more complicated than the first case, the one dimension, but it is the same concept. However, the derivations are given in the slides, but I'm going to skip them for today. But I will check if there's something needs to be commented here. So you can see it. This is the expectation step where you estimate the likelihood data based on the assumptions. You can see it, here it is based on theta L. Theta L means here the parameters at iteration theta, at iteration L, sorry. And then in maximization step, we maximize by assigning the data to the proper distributions or the proper clusters. And of course, the likelihood is always going to be bigger like in each iteration. Okay. In case that you have not only two classes, but you have like k classes, then we can define this z like those z1 until zk. It can be one only for the location of the cluster. So it is actually multinomial distribution data here, or variable. Okay, but we can just skip these until yeah. Here it shows that in case of multivariate normal distribution, again it can be calculated in this way. It is quite similar that we have done here, but here for one-dimensional and here for the m-dimensional, or for the like multivariate distribution. Yeah. Okay. Once we have clustered the data, so now we have data. It was not labeled, and we were looking for clustering the data. So we have, as I said, so we have some kind of data. So it is d-dimensional, and we have here n samples, can be hundreds or thousands or even hundreds of millions of data. And based on what we have seen, we don't have labels here, but we were able to cluster the data. So we have clustered, yes, we have clustered the data and converted them into groups. And in each group that we have certain part of the data. Okay. For example, 3 clusters. And after clustering the data, we need to look to these clusters, and we try to retrieve information or knowledge based on the clusters. It is very similar to data reduction that we have seen, but usually data reduction, as we have seen, that the number of clusters, or the number of the dimension after the reduction should be less than d. Here, actually, the number of clusters can be even more than d. Okay, how? If we assume that this data comes from certain engine, okay, and then let us that we have dimensionality here. Maybe we have like 7 data measurements. So we have the vibration, the temperature of the engine, and the year of manufacturing, and so on. But out of this 7, maybe this data was clustered into like 20 different kind of faults, like fault 1, fault 2, fault 3, and so on. So you can see that the clustering is not the same as data reduction. However, the mathematical basis, they are very similar, but they can be different. The application actually is different. The application is different. Here in the clustering, the data can be clustered like based on the faults, for example. The number of faults can be more than the dimension of the data itself. So we can we can learn after the clustering. This is the first thing. One thing more. What if you have, let's say, you have 100,000 data samples, and out of 100,000 data samples, you have only 100 labels. So you have not all your data are labeled. So you have you are working in certain situation in a company or in your thesis, and you find that the data that you have obtained, but small part of the data is labeled. That you have classes, for example, class 1, class 2, and class 5. You have classification of the data only for 10% of the data, but 90% of the data was not labeled. what to do. One method is to come to the whole data and you cluster them in this way as unlabeled, as unsupervised learning. And then you look, for example, you find most of the class 1 comes, for example, here. Most of a class 2 comes, for example, here. And most of class 3 comes here, for example. This 100 classes comes in this. So based on that, you can use this information to also like classify or to learn your data based on the classification. And you can also like adjust your clustering in order to maximize the number of the same classes to be together in each cluster. So there are a lot of learning methods that can be done after the clustering process. In the slides, I gave several examples, so it's highly recommended that you study those, especially in some like marketing and business applications as well. Okay, yeah, we can start this after the break, so we can have a break like 15 minutes and then we continue. Okay. Hello again. So, okay, in the first part we have seen some clustering methods, and namely the k-means clustering and the expectation maximization algorithm for clustering as well. And still both of them, even they are unsupervised, but still we use some kind of parameters there. So we, for example, we assume the distribution, we compute the means. For example, we try to cluster based on some. Still we have some assumptions there. Okay, in hierarchical clustering, we try to simplify things even more. Here, we instead of looking for some cluster means or say that it has that kind of distribution and find the mean and then maximize the probability and so on. No, we came to the data and we tried to cluster the data based on the distance, like similar data being together. Simple like that. Similar data should be together. And they say that similar inputs giving similar outputs. It is true in many cases. It is true in many cases, but of course, not very accurate if it works. But it can be accurate if you have all dimensions. If all required dimensions are there, it might be work. But and also we are living in time varying universe. So maybe if you give the same input today for the certain system, it might give different output if you give the same input after like a couple of days, because we are living in time varying universe. Even the behavior of people is time varying. Many things before 20 years it was like unacceptable. Today is acceptable. And what is today acceptable, maybe after 30, 40 years becomes completely unacceptable. So you cannot always say that similar data will always give the same output. It is not necessarily true, but it might work if the time period is small. Anyhow, so here they can compute the distance between two data entries like XR and XS as the distance, like Minkowski distance, for example, with b equal to 2, then you can put here square. Or you can also compute with b like a prime number or odd number. If you put b equal to 3, for example, then you will be able also to find which one is bigger. For example, if this is 3, or this is 4, and this is 2. 4 minus 2 is equal to 2, and when you take the square, is equal to 4. But if this is 2 and this is 4, so 2 minus 4 is equal to minus 2, and minus 2 squared is equal to 4. So here it gives you 4, the same measure in both cases, but it didn't mention that XR was larger than XS or XS was larger than XR. So if you use, for example, B equal to 3, In that case, you can also find which one is bigger than the other. Okay? In some applications, it might be useful in some applications. So the idea here is to define some measure for the distance of the data. So you have in your data entry, okay? So you have some data, and then you start to clustering the data based on some measurements of the distance. So you start, for example, to measure the distance between each entry and the others. And how it works, in the beginning they start with, for example, if the data that you have is n samples. So they start with n like groups. So they assume that we have n clusters. Every input as like one cluster. Okay, then they start to apply some merging algorithm. The merge algorithm that you start, for example, the data which belongs to the same distance, they are merged together. Then we start to reduce the number of clusters to the minimum required based on the threshold of the distance. Okay. The distance can be also based on this block city, that is just the absolute value, and you take the summation over all dimensions, as you can see. And as I said, that it can be like agglomerative clustering, that you start with n groups and then you merge them, or it can be also diffusive clustering, where you start with the whole data as one group, and then you start to separate them by measuring the dissimilarity between them, not the similarity. Then also you can measure the distance between two groups, like the minimum distance of the data in each group I and the group J. So this is actually the basic concept of hierarchical clustering. And the non-parametric approach says that data speaks for itself. So usually we don't put any assumptions. Don't say that the data has Gaussian or normal distribution, but try to find what distribution the data carry by yourself, because you have already the data. Since you have the data, why we try to say that the distribution, you have already the data, so we can build or we can find what distribution the data has. So, for example, let us have this probability density function for, it is f of x for single element, okay? This is a distribution for single element, for example. And if you take, what is the probability? Okay, what is the probability that the data becomes, let's say, between x0 and x0 plus h, and this is h. The width is h. Okay. Remember, once you have data and you was able to find the distribution of data, as we have seen before, then like maybe 70% of the problem has been solved. Because once you know the distribution, then you can estimate the parameters of the distribution, then you will have like accurate model for your data. The problem that this distribution is usually assumed or given as assumption. But now, in this non-parametric approach, we try to look to the data and we try to build ourselves that what the distribution of this data, the uncertainty of this data follows what kind of behavior. Okay, so now if you would like to calculate the probability of based on certain distribution of data to be between x0 and x0 plus h, this can be calculated simply like integration from x0 to x0 plus h f of x dx. This is the probability. This is the probability that your data is greater than x0 and less than x0 plus h. You can revise part 2 or but free about the probability theory. And now, if h is very small, we can approximate this as f of x at x equal to x0, at x equal to x0, okay, multiplied by dx, or this difference is, it will be like x0 plus h minus x0, which is h. It will be multiplied by h. Okay? Now, look to this. F of x, and we put here hat to mention that it is the estimation of the distribution at x equal to x0, at x equal to x0, is equal to the probability to x to be greater than or equal to x0 and less than or equal to x0 plus h divided by h. Okay? Because we just divide h here, there. Now, if you have data, and let us say that, okay, I will give simple numerical example here to see how to calculate it. So you have this data x, okay, and this data, let's say it is 1 and 1.2 and 1.4 and 1.7, and then 1.4 again, and 1.1, and then 2, and then 7, and 1, and 3, and so on. Okay, this is the data that we have. Here it is 2.4. Yeah. Now let us that x0 equal to 1. x0 equal to 1, and let us take h equal to 0.5. What is the probability that x greater than or equal to 1 and less than or equal to x0 plus h is 1.5? How to calculate it? Simply, you count how many data you have between 1 and 1.5. So we have this one, 1, 2, 3, 4, 5. We have 5 elements between 1 and 1.5. And the number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 5 divided by the total number n is 10, which means that it is half. So the probability is equal to half. Simply, what it means that the probability, the data to be greater than or equal to x0 and less than or equal to x0 plus h is, you count the number, this means the number in your data, the number that x is less than or equal to x0 plus h minus the number that x is greater than x0, okay, and then you divide it by the total number of data n, and then we have here h, so it becomes like that. So this is the way we calculate it, like in the estimation of the distribution. This is the estimation of the distribution from the data. And of course we can repeat for all x0. For example, if our data x0 is greater than 0 and less than 5, for example, then start from 0 until 5 in this way. How to select h? We can select h either don't to be very, very small, because if you select h very small, you might have like missing, a lot of missing parts here, and also noise and disturbance can affect the result. And also h shouldn't be very, very big, because this will reduce the accuracy. So we need to compromise of h to select the proper way. This is called histogram. This, what we have done here, is called histogram of the data. And this is the explanation for this, but this is at least the derivation of the data. Okay, so in the histogram, you can see that in Octave or MATLAB, you can draw the histogram for any data that you have just by writing hist, this, and then you put the data, and here you put the number of bins. This is the number of bins that you can obtain. of course, which also reflected the edge width. As the number of pins is more, it means that the edge is smaller, as you can see here. Okay, so here with the number is equal to 100, and here is 1000, and so on. So assume that you have this data, and you want to make some to build some algorithms and learning algorithm. You can see that this data, if you assume that it is normal distribution, for sure the result will be not good, because it is not even similar to normal distribution. So actually looking for the histogram of the data can help a lot when you want to build some algorithms, more accurate algorithms for your data input. What's coming next is just some more algorithms in order to improve the result of the histogram, in order to get better or more accurate distribution assumption or estimation of the distribution. Here we use some smooth weighting function, like Gaussian, for example. It is used in order to smooth the distribution. Okay. Also, it is one of the well-known techniques that instead of changing, because when h is fixed, then the number of elements inside the period or the interval h is different. If for larger h we have larger number of inputs, smaller h we have smaller number of inputs usually. Okay, and in k nearest neighbor estimation is very interesting method that h is adaptive, is not fixed, but the number inside, the number of pins is fixed. So usually we fix the number of pins in the interval, but the interval itself, it can be adaptive, as in this KNN estimator. And KNN estimator is one of the very well known and applied techniques in non-parametric estimation, and also in non-parametric learning as well. So you can see that here you can just specify k, and then d, the number can be the h is varying according to the data itself. It can be also smooth with the window, with a smooth window, like in this way. Okay, the data in the estimation of the distribution, it can be also generalized to the multivariate distribution. And in that case, we need to use vectors instead of the single element. However, of course, there are a lot of precautions should be taken into account when we work with this multidimensional or multivariate, because usually we will need a lot of data in order to fit the data to get accurate result. Yes, the decision trees, this is the last topic for the non-parametric estimation. We might not have enough time to complete it for today, but at least we introduce it, the concept here. So the concept of the decision trees is based on looking to the data. Usually it is supervised non-parametric method. It is a supervised method, but non-parametric. We don't have to put any assumptions in the beginning about the data that we have. We don't put assumptions about distribution or, for example, clusters or anything. But of course, it is supervised method. So it means that we have labels, like in this one. We have the labels already, and then we want to to see how the data could be expanded in order to be simple to follow, and also to increase the interpretability of the data. So the interpretation of the data is very, very important in the decision trees. The interpretation means that you have a lot of data. For example, for certain, as the example of the engine, we have measurements about the vibration and the temperature and so on. Then we have certain classes of the faults. So this is fault 1 happens with this data, and then we have fault 1, and then we have fault 2, fault 3, and so on. Yes, many times it is difficult to have some good interpretation why fault 1 happened with this input, and why fault 2 happens with that input. Even, for example, this was different or was similar or so on. So the interpretation of the data is one of the very, very important thing that we need from machine learning. That a lot of data, and we got some rules. Rules could be generalized, after that could be applied in improving. For example, if we have certain fault happen, and we have good interpretation for the reasons for that fault, then we can improve the design in order to fix the problem, for example, or at least to build more sophisticated like maintenance schedule for certain engine and so on. Okay. So the interpretation is one very important application of the decision trees, and the decision trees work simply by from the root until leaves. Okay, so it is like tree, start from root, and the root here, for example, in this example, you can start with any of these like features or attributes. For example, if you start with attribute x1, okay, and then, for example, if x1 it has like 4 values, it can be like value 1 or 2 and 3 or 4. Okay, then 1 or 2 or 3 or 4, then you can see, for example, this is x1, it can be divided to 1, 2, 3, and 4 elements. Okay, then you come to x2. x2 can be divided, let's say, into 3 elements. Then we come to x2, which can be divided into 3 elements. So it is 1, 2, 3. x2 also 1, 2, 3, and so on. Okay. For each one, for example, if a branch 1, you can see how many outcomes comes with branch 1. So this will be the probability that you being in branch 1, and this is the probability of being in branch 2, and so on. Some values can be not like discrete, but it can be numeric. In that case, you can have like some threshold. Like in this example, on the slide, we have like numeric values, but here we decide to have this threshold W1 and the threshold W2. And you can see that here x1 greater than W1, then we have 2 options. It is either yes or no. And usually in the numeric result, you have usually this like binary decision. When you put some threshold, greater is yes and lower is no. So it is greater, so it is yes here, and here we have no. And then we come to x2, the second attribute here. Is it greater than W2? Yes. Then we got this one. No, we got this one, and so on. So those called leaves. So generally in trees, we start from root and we ended to leaves. Leaves means that it cannot be divided anymore. It cannot be divided anymore. Of course, this is quite simple here, but the tree can be much larger, and then we can have a lot of information based on the tree. The tree is not unique. Actually, you can generate the different trees for the same table. For example, for this table, if someone else started to the root with x3, not x1, okay, with x3, and he might use different way of classification for this, so he will have different tree. Okay, and then you can actually you can generate, especially if you have a numerical input, then you can generate actually infinity number of possible trees. The number of trees can be infinity, and in that case, which tree is the best one? There are different criteria. One criteria is the tree with the minimum size. This can be the best one, or the tree which is more like clear, and the interpretation is very clear for the tree is also another criteria, and so on. So you might have many different trees that you can apply for the same table that you have. The tree can give you a lot of information, and you can go quite deep in order to have like deep knowledge about the data itself. However, the error variance can be high because trees is easily to get like overfitting. How to solve the problem? Then we build forest. It is called like random forest learning. It is based. The idea is very simple. Instead of building one tree, okay, you can generate many trees with different criteria, and then you take the average. When you take the average, then we have this random forest learning process. Okay, so this is the concept of the tree itself, and okay, we still have a few things, but I do prefer to stop here, and then we complete next lecture. Thank you.